quiet. Hey guys, we are going to do our third lesson of section 11-2, trying to finish up the stuff with vectors. So there's a couple of questions left over from yesterday, kind of, sort of, and then we're going to learn some new items about how to use like your velocity vector and stuff like that. So that's what we're going to accomplish today. I noticed something about the note paper. It seems that the like the letters, like parts A, B, C, D, did some weird like autocorrect things. So just follow along in the order and you guys will be totally fine. So let me go ahead and get my PowerPoint pulled up and we'll get that started. Hope you're having a pretty good day. And hope the YouTube option is working, and let's get started. So fun little title for today. I think we're having like a movie/TV theme, if you haven't noticed. So we're going to have return of the vector today. And so we're going to talk about vectors in the plane. Remember, guys, you can pause this at any point. So if you feel like I'm going too fast, then you could be like, whoa, 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 and you could back up. So that is the beauty of having it on YouTube. Okay. So example number 7, we're just kind of like dive right in. Example 7 and example 8 on our notes are sort of carryovers from yesterday's lesson. And then we have our displacement and our distance traveled at the back of the notes, which will be sort of like newer things, okay? So we are going to use this position vector, and it says it's R of t is going to be the position vector of sine of 3t and then cosine of 5t. And then we're going to find the velocity and the accelerations and then determine the path of the particle. So velocity, we know we're just going to do the derivative, and we just do the derivative in its components. And so we're going to use a little bit of chain rule. And so the velocity vector in vector parentheses is 3 times the cosine of 3t and then comma -5 times sine of 5t. Pretty simple. The acceleration vector is going to be the derivative of that. And so we're going to go -9 times sine of 3t and then -25 cosine of 5t. And that's it. It asked us to also graph it and figure out its path. I think what's probably best for this one is to just put your vectors sort of like in parametric mode, because technically, guys, when we have our components, right? Okay. When we have our components, this guy right here would be like the x value, and this guy would be the y value, like on each of these. This is the x, this is the y, right? This is the x, this is the y. So it's all the same sort of thing. So we're going to do it in parametric mode. Of course, you need to be in radians. Since we are graphing the path, we do need to graph the position, guys. So this is the guys up here. This is what we're working with, the position, guys. That's circle is way off, but you guys know what I'm doing. And we just put each of those into parametric. The t values, it will just complete one cycle between 0 and 2 pi. I think the x values don't need to be very big. They really just range from -1 to +1, and the y value is the same thing, -1 to +1. And then I just did the steps as pi over 48. You could also do pi over 96. That'll like get a lot of the values. And if that was enough time to stall for you to put that in your graphing calculator, this is what it looks like. Isn't that crazy looking? Wow. Okay. That is the path of the particle. What is nice is that you can also watch it being traced and like watch its path, which I think is pretty cool. So if you did not do that in your graphing calculator, you should pause the video and do that yourself. Okay, so then jamming on to example number 8. Okay, so now we're saying there's a particle and it's in an elliptical path. So they're flat out telling you that this is an ellipse, you guys. Okay, so it's an elliptical path. And then here's its position, right? So we know that the position coordinates are going to be the same as the position vector. So when we go to part A, which on your note packet, it does say part E. So silly. Some weird autocorrect thing. I don't know what happened. Is going to be the acceleration, the velocity and acceleration vectors. So we're going to do the velocity vectors just by components. And so we're going to get the velocity vector is pointing parentheses for cosine t and then -2 sine t. Great. Love it. Derivative of that for our acceleration vector is going to be -4 sine t and then -2 cosine t. Great. Love it. Very straightforward. Then for part B, Again, it says F on your note packet. Okay, we're going to find the velocity, acceleration, speed, and direction. Folks, that's 1, 2, 3, 4 things at the specific time of pi over 4. So we're basically doing a lot of plugging in of pi over 4 to all the different things and then writing the spots, okay? So the velocity at pi over 4, we know cosine of pi over 4 and sine of pi over 4, if we're thinking about our unit circle, is both rad 2 over 2. So 4 times rad 2 over 2, negative 2 times rad 2 over 2 gives us 2 rad 2 and then negative rad 2. So there's the specific velocity vector. The acceleration vector, we'll go ahead and plug in pi over 4. So we're going to plug in pi over 4. Again, sine of pi over 4 is rad 2 over 2, cosine pi over 4, rad 2 over 2. That turns into negative 2 rad 2 and negative rad 2. Lovely. I ran out of space on this screen, so to find the other two things it says in the notes speed and direction of motion, we're going to go to the next slide. So the speed, remember, speed, guys, is not a vector. It is a scalar quantity, right? So it's the magnitude of the velocity vector. So I'm going to take these pieces right here, these numbers from the velocity vector, and plug them into the Pythagorean theorem. So that's where the 2 rad 2 comes from and the negative rad 2 comes from. I'm going to square them, add them. That gets me 4 times 2. This guy is 8. This guy is 2. 8 plus 2 is 10. So rad 10 is the speed. Okay. What's the direction of motion? We're going to take the direction of motion is basically the velocity vector and then divided by the magnitude, or you can think of 1 over the magnitude, okay, which we just found. It's rad 10 in front of your velocity vector. And so that's exactly what I did. I took my velocity vector values of 2 rad 2 and negative rad 2 and divided them each by the rad 10. I am going to clean that up just a little bit. No, I'm not going to clean that up just a little bit. I'm going to leave it just like that. If you want to, you can clean it up. But remember, this is calculus. So that cleaning up, rationalizing the denominator, doesn't even matter. Okay, so it's just totally like this. All right, part C of the question says we're going to sketch the path, okay? So basically, it told us that it was an ellipse at the beginning, and so you could sort of like parametrically, kind of like what we did in the first unit, think about what that would be for all the coordinates, okay? And so, or I could think about eliminating, quote, the parameter and doing basically like what we did in the last section. It's this ellipse. I kind of like knew that's what it was going to be, right? Where the X value would be, like 4 on each side and the Y value would be 2 on each side, mostly because this guy right here, right, there's a 4 and this guy right here, there's a 2. So I kind of just knew that was going to happen. And here's my ellipse. Now it does say to show the velocity vector at the point 4, 0. So the point 4, 0 is that spot right there. So at that spot right there, what's like happening to the vector, right? So what we want to do is we want to set each of those values that is its position equal to the coordinate. So we have 4 sine of t being equal to 4 and 2 cosine of t being equal to 0. And we want to see like when does this happen or what happens here. Okay. So when can we get, oh, I gave it away, but when can you get the sine of 4 sine of t to equal 4 and 2 times the cosine of t to equal 0. And that happens when t is pi over 2, right? Because then the sine value would be 1 and the cosine value would be 0. So then if this is the time when it happens, right? Like here's the time. This is the t value when it happens. What would be the velocity vector? Okay, so we have to think about where's my velocity vector and plugging in the time of pi over 2. So we get 4 cosine of pi over 2 and then negative 2 sine pi over 2. Cosine of pi over 2 is totally, I'm plugging it into the velocity vector, right, guys? Cosine of pi over 2 is 0. Sine of a pi over 2 is 1. And so we get 0, negative 2. If I were to draw that vector at the point that we had identified earlier, this point right here, okay, what would that look like? It would look like this. If you put this in your graphing calculator and you sketch it, okay, and you sketch it, you will see that point, like that the drawing is going that way, which makes sense that that's the velocity vector. So then part B, I am going to flip back to the picture on part C really fast, but it says, does the particle travel clockwise or counterclockwise around the origin? Well, let's go back to the picture. Okay, if we knew nothing else but this picture, okay, I knew that you knew that at this point right here, my velocity vector was going this way. Wouldn't it sort of follow and make sense that it would be going this way? Right? Because that would make sense for the vector. Okay, that direction is traveling in a clockwise manner. Okay. And so there it is. Those all of our answers for that. So let's turn to the back page. Okay, so turn. Maybe these notes are a little bit shorter than the days before. And we're going to write some fun stuff. So we're going to talk about now displacement and distance traveled. So we haven't talked about that yet. Let me just get rid of this for a second. We have talked about velocity vectors, acceleration vectors, position vectors, but we haven't, and we talked about speed, okay? But we haven't talked about displacement or distance traveled. So that's what we're gonna focus in right now. And again, the notes, the numbering and weird, it's all off. Just go in order, you guys will be fine, okay? So this is like the setup, okay? So this is just saying that suppose that a particle moves along a path, so the velocity is given by this. You will notice that every question we've done so far started with either the position coordinate or the position vector, which are the same thing, right? This is starting with the velocity vector. Oh, okay. So this is starting with the velocity vector. So like think to yourself, velocity vector, okay? So what happens is the displacement when from time A to time B, whatever that is, okay, is given by the vector of the integral of the velocity part with the x and the integral of the velocity part with the y component. And so this is your displacement, right? So this is like how far it traveled from time 0 to time 2, time 0 to time pi over 4, whatever it is. And you do the integral of the velocity vector, okay? You are going to get some numbers, because this is a definite integral, right? Because we have the A and the B, these are definite integrals. So this is going to be a number and this is going to be a number. So what are we going to do with those numbers? If we wanted to find like where the particle or whatever it was ended up, we would add your displacement answers to your initial. Okay, so your initial position vector at those times, and then you would get the final position. So that's what you're writing in the note, that we add this vector to the position vector at the time A to get the final position at time B. So wherever time you're starting at, what's the position there, and then we'll add the displacement. Okay, then total distance traveled. Okay, total distance traveled actually looks like this. It is, and this is interesting, notice that it's not a vector. Folks, this is not a vector. Distance traveled, okay? Remember, it doesn't matter if you're walking backwards or forwards. If I say, oh, I walked 2 miles today, which I totally have not done, you guys. Seriously, long distance learning is a lot of sitting down. Okay, sidebar, JK, I'm back. Okay, so if I were to say I walked 2 miles today, would it matter if I like walked forwards or backwards? No, it would still be 2 miles. So this is not a vector. Again, this is a quantity. Okay, so this is a quantity. So we're going to take the integral of the magnitude of the velocity vector, and we know that this is going to be this is not a number. Okay, so what is the magnitude of the velocity vector? It is, remember, like the x component squared plus the y component squared. You know what's really interesting, guys, is this velocity. Let me think for a second. Let's make a connection. Velocity is the derivative of the position. Folks, we are doing the integral of the x component's derivative squared plus the y component's derivative squared. You should be like, wait a minute. This looks very familiar. It is very familiar. Okay, this is the same formula as the length of a parametric curve. It's the same. Oh my goodness. This is amazing. One less thing to really memorize. Just apply. Oh, I love mathematics. So great. Thanks, calculus, for giving me something that I can memorize because I already did it. Yay. Let's put this into play and do an example. So example number 9 says, is giving us, again, it's starting us with the velocity vector, folks, the velocity vector. And here it is. Okay, they just made it up. At time 0, the particle is at the coordinate. Folks, this is an initial position right here. Oh, okay, I see. I'm going to use that in a minute. Find the position of the particle at time 4. So we're starting at time 0. We're going to time 4. What is happening? Okay, we are going to find the initial plus the displacement. Initial, 1 comma 5. What's my displacement? We just wrote on our notes that what we're going to do is we're going to now find the integrals. So we are going to take the integral from 0 to 4 of the x component of the velocity vector. T minus 3 pi cosine pi t, and then dt, and then the same thing, 0 to 4 of the y guy, 2t minus pi sine pi t dt. And that's what we're going for. So here we go. I am just going to tell you that what you could do, you can maybe put it in your calculator. Woo, woo. Gotta love a good calculator question, right? Or you could do it by hand. Probably I would just have tossed this in my calculator. Regular mode, just did it with x's, boom, done. The x guy happens to be 8, and then the y guy over here happens to be 16. And so what that means is I'll add that to my initial coordinate, and my final position is the coordinate 9, 21. There it is. Okay, so a little bit of thinking, a little bit of calculator work, boom, done. We have the new position. Part B of the question, which I know it says part F on your notes, says what's the total distance traveled? Okay, so we're putting into play what we just wrote down, how to find that. So it was the integral of the magnitude. Got it. Okay, so total distance is going to be the integral from 0 to 4 of the velocity, guys, right? At, right, a particular number. So this is a hot, not at a particular number. I was lying to you before. What I said about 10 seconds ago, scratch that, rewind, start over. Total distance is the integral of your velocity components, right? The x guy and the y guy. So I just grab them from the question right here. Just grab, there's the x guy, there's the y guy. I put them in here and I'm going to square them. I'm not doing that by hand. No, I don't think so. So you're going to grab your graphing calculator, pause the video if you want to, put it in your graphing calculator, and then it's going to spit out a number. And the number it spits out is 33.533. That's it. That's how the total distance traveled is. Love it. Got it. Got to do some work on my calculator. Me and my calculator, super besties right now. So fun. Okay, we are going to do one more example. So in number 9, the one that we just did, we're going to determine the path of the particle. Okay, so to determine the path of the particle, that means I need to figure out let me think. I need to figure out a position vector, okay? So I only started with the velocity vector. That's what I have right now, the velocity. So you're thinking in your head, just in general, calculus general form, how do you go from a velocity to a position? You take the antiderivative. So folks, that's exactly what we're going to do, okay? So we are going to figure out how to graph this. The x component is going to be the antiderivative of t minus 3 pi cosine of pi t. And then we're going to have to think about plus c, and we'll do our initial condition. So let's do the antiderivative here. The antiderivative is a 1/2 t squared, or t squared over 2, and then minus 3 sine of pi t, right? Because we would have, if we were doing the chain rule, we would have multiplied by pi, and then we do plus c. We know that at the time of, well, let's do the y guy next. Sorry, I got ahead of myself. I always rush these things. So silly. So we're going to do the y guy. So that's going to just be a t squared and then cosine of pi t plus c. We know the initial condition at time 0 was 1, 5. So that's basically what happened. We're going to let t be 0, right? T is going to be 0, and then we're going to solve for the c values, okay? So right here, the x value is 1, so it ends up being 0 minus 3 times sine of 0. Sine of 0 is 0, and so in this case, c happens to be 1. On the other guy, let's see, we'll plug in 5 equals this. And this is interesting because The 0 squared zeros out, but cosine of 0 is actually 1. And so what that means is that C is 4 right here. So what we got is the position vector is the antiderivatives, right? Here's your antiderivative, and then plus C. The antiderivative, and then plus C for each of these guys. And then what we're going to do, so let me just read it off to you. It's a 1/2 t squared minus 3 sine of pi t plus 1, comma, t squared plus cosine of pi t plus 4 in the vector parentheses as your position vector. Now what we're going to do is we're going to put this in our calculators and we're going to try to, okay? So what I want you to do is I want you to graph it in parametric, right? This is going to be your x component. This is going to be your y component. Your time is going to be from 0 to 4, because remember back in the question 9, it says like question 9 A/E, find the position of the particle at time 4. So we want to go all the times from 0 to 4. Our steps are going to be pi over 48. And then I have no idea what this looks like. So what I did, once I put all that stuff in and changed my window, all that good jazz, I went ahead and did zoom fit. And the weirdest graph happened. When you watch it graph, it's actually really cool. It looks like this. Isn't that the craziest, coolest graph? Like, I can't even imagine. Like, I would never be able to make that. How cool that you can make something that amazing in using like vectors. It's way super cool. So in summary, what we've learned today, guys, we did a little bit with our acceleration vectors and our velocity vectors, and then we did some stuff where they start us with the velocity vector, and then we had to go find displacement and distance traveled. So we had to do some integrals and all that good stuff. So this is your homework assignment. Love it. Beautiful. There it is. I'll totally post it in Google Classroom. Join me for office hours if you want to. Today we had our first office hours. And it was kind of amazing. It was great. People came by and said hi. So you can hang out for a while. I kind of talked to myself, but it was lovely. And so that is it. Okay, guys. So I'm going to pop back on just so you can see my face to be at the end. And there it is. Okay, I think you're going to be golden. It's going to be amazing. We're just plugging along. And yeah, that's it, guys. So I will hopefully see you soon. Bye. I'll see you.